All right, hello, my EM aficionados. So this has been a long time coming. I can't believe it's been nearly, well, more than 2.5 months. This happened all the way back in mid-May. Unfortunately, MSA still hasn't gotten this recording up, and I apologize for that. I've been contacting them regularly about this, but I don't think it's going to happen, unfortunately. So, I wanted to go through this for you and put this up directly on my channel so that you can have it again as a reference if you already saw it. And I know several people contacted me about seeing it themselves because they couldn't get in again because we had the glitch with the Zoom account. So we're going to go through the webinar again. Okay. Full disclosure, I might be a little rusty with this, right? Because I did spend some time going through the slides again to refresh everything before doing this, but this wasn't like how I was right before I gave it back in mid-May. Okay, so I had been prepping for that for literally many weeks. Okay, so with this is kind of a little bit more off the cuff here, but I think we're going to still see pretty smooth sailing here. But just full disclosure here. So, all right. So the webinar was about STEM and today's essential techniques for STEM. Okay, this was the idea I pitched for the MSA committee, and they really liked it, and so that's what I went forward with. So we're going to talk about these essential techniques today. If I can advance the slides. There we go. All right, so just to start out with some acknowledgments, obviously I want to acknowledge MSA for this tremendous opportunity, and in particular, Aaron Johnson. He's the gentleman from MSA I've been interfacing with directly. It's been great chatting with him in particular. I want to acknowledge where I work at the University of Florida, the research service centers in the Herbert Wertheim College of Engineering. I want to acknowledge the two main microscope manufacturers because you are going to be seeing data from these microscopes today. So thank you for this wonderful technology that has greatly expanded our electron microscopy horizons, STEM horizons in particular, over the past several years. And of course, my wonderful family here. So you see the three human components at my brother-in-law's wedding. This was back in fall of 2022. And of course, I always tell people that I have three children, not just one. So, one is a human daughter, but I also have a cat daughter and a dog daughter. So, and of course, what would I be if I didn't mention them as part of this as well? So, all right. So, just a quick mention about the data that you're going to be seeing today. Okay, so if you read my little bio about the presenter, right, you saw in there that I like to watch The Simpsons. Okay, so if you recognize this character from The Simpsons, this is the hack medical doctor, Nick Riviera. So I'd like to think that I'm not a hack, at least not as far as electron microscopy is concerned. But so you take Dr. Nick and you give him a fancy microscope and you get, nice data out, okay? So the point of this is pretty much all the data here, unless I specifically otherwise note it, okay, was collected by me, okay? Samples that I made and the microscope that I actually operated, okay? If that wasn't the case, I explicitly note it, okay? I also went to great lengths to specify the microscope systems used for the different pieces of data that were collected too, okay? So you have an idea what microscopes were used in collecting all of this. Okay, so the topic of the presentation was essential techniques. So what do we mean by, or what do I mean? Because this is totally my opinion, okay? How do you qualify a technique as essential? So the way I qualify a technique as essential is it something that you should be able to do on a day-to-day basis at the drop of a hat. Okay, so I don't know if any of you are familiar with that phrase, at the drop of a hat, but that basically means if you do something at the drop of a hat, you're able to do it basically immediately. Okay, so in other words, somebody walks in the door to our facility and says, I need, CS corrected STEM imaging. Okay, I can do that now. Okay, I need high resolution imaging. I can do that now. I need STEM-EDS mapping. I can do that now, right? Oh, and the last graphic, of course, is I need selected area diffraction work. Okay, I can do that now, right? That's what I qualify as essential. Okay, something that you would be expected to be able to address on a day-to-day basis, and basically like immediately. Okay, sort of like if you worked at a oil change place, okay, you would be expected to be able to change people's oil, right? At the drop of a hat when they come in, right? Because you're an oil change place, okay? Just to kind of give you an example, okay? That would be an essential technique, okay? And then if you had something a little more exotic, like, I don't know, changing a certain belt or something like that, well, maybe that's not something that you do as often, right? But because there are techniques that, at least personally, right, I don't think they're quite as essential because they just don't come up as much, at least in the day-to-day scope of operations, okay? But these are the four, actually, as we're going to see here, that I am qualifying as essential. So the basic outline, we're going to introduce and describe each technique, what it is and how it works fundamentally and technically. We're going to see lots of data and application examples. And then, of course, we're going to talk about the justification for why it is included as essential, okay? All right, so the first one is high-resolution TEM imaging, okay? And in my opinion, this one is the most important one, okay? Your ability to not only perform high-resolution TEM imaging, but also to fundamentally understand it and how it works, really provides the basis and the background for all other types of imaging in the STEM, is specifically high-res, okay? So here's a basic schematic of how this works. So we start with a parallel or nearly parallel. It's not, strictly speaking, it doesn't have to be parallel, but static incident beam, meaning it's not moving. Okay, we're assuming our sample is crystalline, so the beam interacts with the sample, transmits through it. As a result of that, when it exits the sample, it consists of basically two components. You have a direct component and a Bragg component. So a direct component means the electron, or that portion of the electron wave, is traveling the same direction as the incident beam, okay? You also have components which have been Bragg scattered, okay? Notice with direct, I didn't use the word unscattered, okay? I have an entire video about this, talking about this, but it is not correct to call those electrons that leave traveling the same direction as they came in as unscattered, okay? Without going into too much detail, okay? Obviously, with the Bragg diffracted, well, that's very obvious, right? The direction has changed, and therefore, right, there's no way that it wasn't scattered, okay? But in the case of direct as well, that does not necessarily mean that there wasn't scattering either, okay? So then, after your beam interacts with your sample, your objective lens post field, in this case, because we're dealing with a conventional image rather than a STEM image, then forms an image of the electron wave as it's exiting the sample, okay? And so that's what we see in the image plane, all the way at the bottom here, okay? So now something interesting happens, though, along the way here. So you see up here with the different rays. So if I follow all of the rays that are direct, what happens is my objective lens post field focuses all these to the same point in the back focal plane of my objective lens post field, okay? Does the same thing with the two different sets of Bragg rays, right? So what I end up seeing here, if I look at this, are actually 3 spots, okay? So this is where our objective aperture goes, is at this plane. And this is also where we see the diffraction pattern from the sample, okay? So that's important as well, okay? So if we look at a schematic of a high-res image, what we see is something like this. So what we see are a series of what we call lattice fringes, okay, each with a characteristic spacing and a characteristic orientation. They will overlap and interfere and produce detail, okay? So if we look at an actual image now, and we're going to see this image again a few times. So high res of alumina or sapphire along 022 bar 1, okay? So in this case, we have a lot of different lattice fringes. I'm not indicating all of them here. That would be very, very complicated to do, but there's several of them here that are included and contributing to the image that's giving this detail, okay? So now, the great thing about high res is that you're forced to really understand the relationship between the image and the DP, okay? Because it is very, very fundamental, okay? So the direct beam in the DP, right, which is usually the brightest beam, okay, this corresponds to delta K equals 0. So delta K, of course, means change in wave vector, okay, change in momentum, or change in direction of my electron, okay? So we can draw a vector from the direct spot to any of the Bragg spots inside of the diffraction pattern, okay? In this case, we're drawing a G vector pair. So we're drawing G HKL and its opposite, okay, minus G HKL, okay? And so the each of these spots in the diffraction pattern is associated with a D spacing, right? Because you see HKL, right, which you think D spacing, and that's exactly the case. So the magnitude of G is equal to 1 over the D spacing, okay? So as G gets bigger, the D spacing gets smaller, and that corresponds to smaller features, as we're going to see in the actual image, okay? So then if we put in an objective aperture, which is at the same plane as the diffraction pattern, that is optimally sized, right, we're excluding some of those spots beyond a certain value of delta K, right? So you can see there's a radius to this aperture, and we can give it in terms of delta K. So this optimal radius is fairly easy to calculate in an uncorrected microscope, which we're assuming here, right? So 6 over lambda cubed C sub s all to the quarter power. So just to give you some examples, if we have a 200 kilovolt microscope with C sub s equal to 1 millimeter, our optimal delta K is 4.4 reciprocal nanometers, okay? Okay? But the key here as well is that because of the Bragg scattering, there is a phase shift that exists between the direct and the Bragg beams, okay? And it's actually this phase shift that is responsible for seeing the lattice detail in the high-res images, okay? So the takeaway here is that for each of these G vector pairs that I include in the aperture, I see a set of fringes with spacing equal to D, okay? And again, D is equal to 1 over G, or G is equal to 1 over D, okay? So that's the takeaway. So you could see, like in this example, there's several of these G vector pairs that are possible. I only indicated the one right here, okay? So if we look at a very simple example here, we just include 2 beams. Now, we would never do this in practice, okay? You would never do something like this in practice because you always want your objective aperture perfectly centered around your direct beam, okay? So we would never do this in practice, but just from a fundamental standpoint, right, this is, useful to illustrate, okay? We have literally only one G vector, period. We don't even have a pair at this point, okay? So if we look at the 2 beams, we can characterize the direct beam and the wave associated with it as this. Okay, so it has an amplitude psi naught. Okay, and then it has a complex exponential phase factor. Okay, and if we look at the Bragg beam, it has its own amplitude psi g, and then the phase factor term is similar to that for the direct beam, but you can see that inside of the complex exponential, we have added in g dotted with x plus y. Okay, so that is the phase difference, that term, the g dot x plus y. That is the phase difference for the Bragg spot compared to the direct spot. Okay, so there's your high-res image, right? You see one set of lattice fringes, and it's very, very easy to show that your intensity in your high-res image, because that's just simply the modulus squared of the total electron wave, which in this case would just be the sum of the individual electron waves, right? One for the Bragg beam, one for the direct beam. You get something like this, okay? So you see sinusoidal oscillations with periodicity equal to 1 over d, okay? Or in other words, the spacing between the fringes, right, between dark fringes and light fringes is equal to d, okay? So, and also, right, we see because we have g dot xy, okay? So if I go along the y direction, okay, well, y is always perpendicular to g, so that's always going to be 0. Okay, so I only see the oscillations along the x direction here. Okay, so the fringes run perpendicular to g in this case. Okay, and again, the fringe spacing is equal to 1 over g or equal to d. And again, the spacing means between subsequent peaks, okay, or subsequent troughs, meaning bright fringes or dark fringes, right? Bright to bright or dark to dark. That would have spacing equal to d. So now if we look at a more typical example where we're including 7 beams and we do have the aperture now centered, okay, this gets a little more complicated, and we actually saw this already previously, okay? So if we go through this kind of step by step here, or I should say Bragg beam pair by Bragg beam pair, if that makes any sense. So if we look at the G1 minus G1 pair, okay, so those are red. So again, they run perpendicular to G. And if we look at the G2 minus G2 pair, again, perpendicular, and they run at that. And then G3 minus G3, which is yellow, okay? And you can see, now these are fairly close in terms of the spacing, but they are a little bit different. They're not all the same, okay? Hopefully that's kind of obvious to see in the picture, but they are fairly close in the spacing. But strictly speaking, they're not equidistant, okay? And then you can see what happens, right, as those fringes overlap and interfere, I get detail, okay? But again, same idea. Each pair, G minus G pair, yields a set of fringes with spacing equal to D. They overlap and they interfere and they produce detail. And so this detail is actually very similar in appearance to atomic columns, okay? So this gets us to this first question, okay? And one that comes up very often in high res, especially to people kind of new to this kind of imaging, is, are we actually seeing this when we're doing a high res image? Are we actually seeing atomic columns, okay? So in high res, are we seeing the true, or not necessarily columns, but the true atomic structure? Is a high res image really a picture of the true atomic structure? So we have 2 examples of this, okay? So we have a high res image of silicon along the most studied zone axis ever, 110, okay? And so here's your high res image. And so now if I superimpose the projected silicon structure at the same magnification as the image, okay, I see something like this, okay? And so you can see that based on how I've placed the model here, it doesn't look anything like what I'm seeing in the actual image, okay? I could have, and just to be clear, I don't even know if this is the correct placement for this, okay? This could have just as easily have been placed with the silicon dumbbells over the bright spots instead of the dark spots. I simply put them over the dark spots because it makes it easier to see. But the point is, right, the image looks nothing like the actual structure, okay, really, right, if we're being honest here, okay? If we look at the case of the alumina, it's even more dramatic, okay? So now we're looking at the 0 to 2 bar 1 zone axis. Now we have 2 different types of atoms, okay? And so you might be tempted to think here, because we can actually see in the alumina kind of 2 sets of dots, right? One that's brighter than the other, okay? So you might think, oh, maybe, well, that's aluminum and that's oxygen, right? So, but if we actually impose the projected structure at the same scale, again, it doesn't look anything like we see in the high-res image. And again, I don't even know for sure if that is the correct placement of the projected structure, okay? So again, even though the fringe interference gives detail that looks like atomic columns, okay, you have to be careful here in knowing that that's not actually what you're seeing, okay? High-res images are not equal to the true atomic structure, okay? Unfortunately for us, okay? But that does not mean that we cannot get useful information even at the atomic level from a high-res image, because we still can, okay? We still can do this. So one of my favorite examples of this is actually using high-res to analyze misfit dislocations, okay? So if you're doing mismatched heteroepitaxy, in the case here, you've got 3,5 semiconductor growth, and you're growing indium arsenide and timonide on indium arsenide, and the indium and timonide arsenide is a little bit wider lattice constant than the indium aluminum arsenide. So it makes sense that you're going to have to accommodate that mismatch with misfits at the interface here, okay? So if we prepare a sample and we are viewing along an appropriate zone axis to see these, and that's important, okay? So in this case, we're again using 110, which really is the most useful zone axis to do this with in the case of 3,5 semiconductors, okay? That's pretty much always the most useful zone axis for viewing these. Okay, you can see here that we can actually see 3 misfit dislocation cores right here, okay? So we can clearly see, right, the disruption to the lattice structure as a result of the misfit dislocations, but that's not the only thing we can do. So if we blow one of these up a little more, we can actually perform a Burgers circuit and figure out the Burgers vector for the misfit dislocation, okay? So in this case, the dislocation is into the page, right? We're looking along the line direction, if you will, okay? So if we start up here, right, and we go down this many points along the lattice fringes, and then we go over here, the same number, okay? So in this case, we're going 1, 2, 3, 4, 5. We do the same thing here. We're going 1, 2, 3 and a half, right? Just like we did on the left, okay? And then we have to go the same distance back over. So we go 1, 2, 3, 4, 5. But you can see now we're not back at the start, right? Because we have a misfit dislocation. So this extra here is the Burgers vector, okay? So we can actually use this to figure out the Burgers vector associated with the misfit dislocation. All right, and here's another great example of this. So this is one of my favorite images that I have ever collected, because it was just so rare to actually see particles oriented like this. So this is a 5-fold twinned gold nanoparticle that is viewed along the just perfect direction to see the twinning. And again, this is, should have indicated this probably, but this is 110 for the gold, okay? So you can very clearly see right here the 5 boundaries, okay? That ends up happening just perfectly, because if you add up the misorientation angle between the individual grains, it turns out that it adds up basically just perfectly to 360, and so that's why you end up with this 5 twin structure in gold, and also in other similar materials that have a similar structure, right? Gold, of course, has the FCC structure, okay? So we can use this to directly image, right, twin boundaries here, okay? The other thing to note too is that if I look at the fringes in the gold compared to the surrounding carbon, which is amorphous, I see some pretty substantial changes, okay? So in the gold, we have spatial or lattice fringes that are spatially ordered, okay? Meaning there's order to the oscillations, right? Very obviously, there's strong ordering. But if we look in the carbon, we also have oscillations of the same scale and magnitude, but they're disordered, okay? They don't have the same ordering that we see in the gold, because the gold is obviously crystalline, carbon is not, okay? So this is another thing we can do with the high-res image, is we can use this to ascertain, right, just at a more basic level, is this crystalline or is this not crystalline, okay? So very clearly the carbon is not crystalline, okay? So HRTM is essential, okay? In my opinion, this is the basis or the building block for all other types of STEM imaging, is you have to be able to do this, and you have to be able to understand it, okay? So from an operational consideration, this is really important because it gets you comfortable with doing things like comma-free axis alignment, which I do have a video about as well, how to center your apertures, how to correct astigmatism, how to properly focus. If you're working with single crystals, you have to learn how to optimize or fine-tune zone axis alignment to make sure that you get the best possible high-res image. So all those high-res images I was showing you of the single crystals were very, very well aligned with the desired zone axis, okay? And then there's fundamental considerations, right? So being able to understand the relationship between the DP and the image is critical, because that will come into play lots of other times, okay? How you interpret the data, right? We saw that, you see these lattice fringes, they don't necessarily give you an intuitive picture of the structure, okay? And of course, how the microscope affects that. And the nice thing about high-res is that it's very accessible, okay? The only requirement really is that you have an instrument that's operable in TEM mode, okay? And the vast majority of STEMs available today, this is, unless they're not configurable as TEMs and only as STEMs, they can do this, of course. So it's very, very accessible technique. All right, so moving on, the second technique is selected area diffraction. Okay, so we saw this diagram before, talking about high res. So if we're talking about generating a diffraction pattern, okay, again, we have the parallel incident beam, interacts with the sample, comes out as direct and Bragg components. My objective lens post field then focuses the rays traveling in the same direction to the same spot in the back focal plane, and that's where I have my diffraction pattern, okay? So I end up seeing something like this, okay? So each one of those spots corresponds to Bragg diffraction from a set of planes, okay? The only exception, of course, being the direct spot in the middle, okay? Right? And again, that corresponds to no net change in momentum or wave vector, right? That is the origin of our diffraction pattern, if you will, which we call delta K equals 0. Okay, so this again is important because we have to understand now, right, the role of the microscope and how we are able to go between what we call image mode and diffraction mode, okay, which is very, very powerful to be able to do, okay, to be able to literally, with the push of a button, be able to see an image, and then if I wanted to be able to see a diffraction pattern, okay. This is one of the really powerful aspects of STEM, okay. So on the left, we have a very simplified projection system or image forming system of an STEM, okay? So you have an objective lens post field, and then one intermediate lens and one projector lens. Now in a real system, you're gonna have way more lenses than does, okay? I think you might end up having 4, if not 5 more lenses than this in your image forming system, okay? So yeah, just a little note on terminology. So basically anything below the objective lens, this is usually given the term of the projection system, okay? If you include the objective lens in that, you can call that the image forming system, okay? But that's basically everything that happens, quote, below the sample, okay? Everything above that is what we call illumination, okay? So right here, this is the entire imaging system, okay? If I only considered the intermediate and projector lenses, that would be the projection system itself, okay? So anyways, right, if we're forming an image, okay, our objective lens, it forms the image of the sample, okay? And then here's that first image of the sample. The intermediate lens then magnifies it, okay? And it forms an image of an image, and then my projector lens magnifies it again, okay? So this is how we're able to generate like million X magnifications, okay, is by having all these different lenses in the projector system. Your objective lens, believe it or not, in terms of its magnifying capability, is really not as impressive as you might think. I think it's only on the order of something like 50 to 100x, okay? So it's really not very strong or as strong as you would think, just in terms of its magnifying power, okay? Even though it is the most important lens in the microscope, okay? So if we want to instead see a diffraction pattern, so a diffraction pattern, again, is right here, but as you can see, we're not seeing that on the final screen here. We're seeing an image, okay? What we have to do is make a tweak to the intermediate lens, okay? And specifically, we have to weaken it. So if we weaken it, what happens then is we end up selecting the back focal plane of the objective lens post field as the object plane for the intermediate lens. So then nothing else changes in terms of the projector lens. So now instead of an image of the specimen here at the projector lens object plane, I have an image of the objective lens post field back focal plane, or the diffraction pattern, okay? And then the projector lens then forms another image of that, okay? Same idea, right, behind how we can increase the magnification of our diffraction patterns as well, okay, through manipulation of the lenses in the projection system. So that's how we're able to actually see a diffraction pattern. So then the other twist on this is that we also have the ability to field limit the diffraction pattern, okay? So by field limit, what I literally mean is you are limiting the area that is contributing to the pattern itself, okay? So we see over on the left, this is just without any field limiting, okay? In fact, you could say you're field limited by just the area you're illuminating by the beam, okay? So if we look at something else here, so if we then go to the objective lens post field image plane and we put a selected area aperture in here, okay? So in this case, I have it centered over the right side. And then if I follow the rest of the ray diagram, what I see here, okay, is that the only part of the sample that is contributing to the pattern is up here on the left, right? So if I trace these rays back to where they came from the sample, you can see that they all came from right here, okay? So I'm not seeing any other contributions from where the beam is hitting on the sample, except from right about here, okay? So this is a way that we can isolate the diffraction pattern from different areas in our field of view, if you will, okay? This is what we call selected area diffraction, okay? And now, obviously, the reason, of course, we have to put the aperture here, we can't put it here at the sample plane, obviously, because there's a sample. So, right, so we put it at a conjugate plane, which is the objective lens image plane instead, and we can accomplish basically the same result. Okay, so there's your contributing area, right, just as I indicated. All right, so what's great about this, right, So if you have a small cluster of a powder, right, nanoparticles, okay, ideally, right, the best way to do phase analysis on a powder is with X-ray diffraction, no question about it, okay? But the problem with X-ray diffraction is that you need enough material in order to do it, okay? With selected area diffraction, you don't need much material at all to do that, okay? So you can use a very small volume of material to do this, right? So you can see, this is a cluster of sodium chloride nanoparticles, okay? And we're acquiring the selected area diffraction from this, and we can see fairly continuous rings here, right? Indicative of, presumably the rock salt crystal structure that we have here. Excuse me, I'm just getting a drink here really quick. Okay. We can isolate this even further. Okay, so typically you can field limit down to around a quarter of a micrometer or 250 nanometers. Okay, but this is a calcium lanthanum sulfide particle that's in the micro scale. Okay, and again, putting in our SA aperture, and we can isolate the diffraction pattern from that particle alone. Okay, if we have a um, a multi-grained material. Okay, so this is the same material, calcium lanthanum sulfide, and we see 4 grains here, right? Very obviously. So we see the boundaries between these grains. So we can isolate the diffraction patterns from each of these grains, right? As you're seeing here. Okay, and we can use this to determine the orientation relationship between the 2 grains. Okay, so this is a way using diffraction to characterize grain boundaries, if you will. Okay, at least at a coarser scale, right? This is obviously not like an atomic level characterization, but this is like a coarse orientation characterization. Okay, what zone axis, what planes? Okay, we can do this with diffraction. Okay, we can also use it to evaluate the crystal quality. So this is a composite material, and it has some grains of zinc sulfide in it. Zinc sulfide, of course, has the zinc blende crystal structure equilibrium in its equilibrium, okay? But it can be highly defective depending on how it is grown and processed, okay? So if we collect the selected area diffraction pattern from this, okay, we see something that looks like a single crystal pattern that has some additional features in it. Okay, so again, note the zone axis, right? This is 110, which I mentioned before, right? This is what's usually the ideal zone axis for viewing materials like this. So you can kind of see how there is a sort of skeleton of a single crystal pattern here. But what I'm also seeing are these streaks, okay? I'm seeing these streaks along this direction in the diffraction pattern, okay? I'm also seeing some spots that are reflected across this plane right here, okay? So I'm seeing some spots that are the result of being reflected back over this, okay? In both cases, this is indicative of the presence of twinning and stacking faults, okay? When you're seeing this streaking and when you're seeing the presence of these reflected spots here, okay? So we don't see like a nice regular array of spots here, okay? So it's a way to evaluate the crystal quality here, okay? And to see, what do we have going on here, okay? So selected area diffraction is essential. It is the fundamental structural analysis method. It allows us to obtain the site-specific crystallographic information with the benefit of a parallel beam, which I'm not going to get into too much detail, but there's a lot of challenges with trying to do something like this with seabed, which could be an entire talk in and of itself. Okay, but there's a lot of benefits to doing this specifically with a parallel beam as opposed to a converged beam, and using selected area diffraction allows that. Okay, we can do phase analysis with very small volumes. Sorry, we can do structure orientation we can determine crystal structure as well as the orientation relationships. We can look at grain boundaries, and we can also evaluate the crystal quality. Okay, and again, this is very accessible. Pretty much every modern STEM is going to be able to do this. Okay, they're going to be able to do selected area diffraction work. Okay, so moving on, we have CS corrected HAADF-STEM imaging. Okay, so you notice I didn't just put HAADF-STEM imaging, I put CS corrected HAADF-STEM imaging. Okay, so we're going to get to that part specifically here in just a minute. Okay, but what is HAADF-STEM imaging? I'm sure many of you are already familiar with this, but we start with a probe, okay, and we illuminate it on a sample. So the probe is a converged beam. It's characterized by some semi-angle of convergence, which we call alpha. Okay, so we're drawing a line through the probe here, okay, and then we're scanning it along on the sample surface. So as it interacts with the sample, it generates a seabed pattern, okay, and then that seabed pattern is projected onto an annular detector or a ring-shaped detector. Okay, and so by manipulating our projection system, we can magnify or demagnify the seabed pattern to give our detector a certain collection angle range. Okay, so there is no hard, fast rule with this. Okay, but generally speaking, when you're talking about HAADF-STEM imaging, you're talking about your inner collection angle of your annular detector being at least 50 milliradians, okay? Just as a general rule, okay? And just to give you an idea, that's about 3 degrees, okay? So it's, when you think about it that way, it's not, we call this high, right? But in terms of STEM, that's a very high angle, okay? But, in terms of actual angle, right, 3 degrees is not very high at all, okay? So as a result, though, of collecting electrons scattered out to these high angles, is that we're collecting only incoherently scattered electrons. So you notice in the seabed pattern here, I'm not seeing any Bragg diffraction way out here, okay? There's basically no Bragg diffraction when I go out to these high angles, okay? So the only scattering I'm therefore collecting is what's called incoherent scattering, okay? And so that has a benefit, right? Because it gives us a type of imaging that is, first of all, robust, meaning it is easily and intuitively interpretable. And it also has the benefit of z-squared sensitivity with the imaging, okay? So those are two really big advantages of HAADF-STEM, if we compare it to like high res, which we're going to see an example of here very shortly. Okay, so if we look at like a nanoscale example of this, so this is a hafnium zirconium oxide alumina coated silicon fin. Okay, and this is a HAADF-STEM image, so you can see all the different layers here clearly delineated by using HAADF-STEM. Okay, because we have the z squared sensitivity, and we have a bunch of variation in the Z, right, with all these different layers that are present here. But we can also go down to the atomic level. Okay, so if we look at strontium titanate along 001, which I will maintain maybe a close second to silicon in terms of the most studied zone axis ever, particularly as it pertains to HAADF-STEM. Okay, so we can use this to actually directly image the structure of the strontium titanate, okay? So when we superimpose the units or the crystal structure on here, we can actually see where we're expecting to see the titanium, or the oxygen, titanium, and strontium. Now you will notice, right, the oxygen only columns actually correspond to just nothing, right? That's just completely black, okay? The reason for that, of course, is you have z-squared sensitivity, okay? The z of the oxygen is much lower compared to that of the titanium and strontium, so unfortunately what happens is that it's very difficult to directly image the oxygen in the presence of the heavy elements, okay? Because of that z-squared sensitivity. There are new imaging techniques that provide a way around that, and at some point I hope to do some videos to kind of address that, okay? But that's why you don't actually see those in the HAADF-STEM image. Okay, so then the question about spherical aberration, well, just to review this here. So now we're talking about the illumination system of the microscope, okay? So the expectation in this case, okay, if we have a perfectly working objective lens pre-field, right, is all my rays come in and my pre-field focuses them all to the same point on the sample, okay? That would be a perfect scenario. The reality is I have something that looks like this, okay? So as the rays traveling farther away from the middle of the lens or the optic axis are focused, they're bent excessively or over-focused, okay, relative to the rays that are closer to the middle of the lens or the optic axis, okay? And this is what we call spherical aberration. What we see, though, is there's a plane of least confusion where we have kind of the tightest, what we call beam waist here, okay? This is what we typically use when we're actually imaging with an imperfect lens, right? Is we image using the beam waist, okay? And so again, this is what spherical aberration does. It causes an overfocusing of electrons that are traveling farther from your optic axis. Okay, so then the relationship between probe size and C sub S, okay? So there's a nice equation here for STEM resolution as a function of wavelength of the electrons and my optimal semi-angle of convergence for my probe, okay? And it's simply 0.61 lambda over alpha, okay? So then if I'm dealing with a non-corrected microscope, right, there's an equation for my optimal value of alpha. So it's 4 lambda over C sub S all to the quarter power, right? So we can see that as my C sub S goes down, my optimal alpha goes up, okay? And then we can also plug and chug. We can get an equation for delta in terms of just C sub S and lambda itself. And we see something that's intuitive here as well, okay? So as C sub S gets smaller, my delta gets smaller. And as my wavelength gets smaller, my delta also gets smaller, okay? So I improve the resolution by decreasing the wavelength and or C sub S, okay? So if I go from, for an example, if I go from 200 to 300 kilovolts, I get an improvement in delta, assuming C sub S is the same at 1.2 millimeters. It goes from 160 to 136 picometers, okay? So that's great, right? The problem, though, is that as I increase the voltage, I tend to get more problems with beam-induced damage, which we call knock-on damage, okay? So this is why we don't just rely on increasing the voltage to improve our resolution, okay? Because as we do that, we have more and more problems with damaging the sample. And if we can't get an image of this sample before it completely is destroyed, well, then that's no good either, okay? So the other approach to addressing this is correct C sub S, okay? And this, of course, is more involved than reducing the wavelength, but is definitely worth the effort, as we're going to see, okay? So anyways, we have an uncorrected system, right? I showed you this before. The rays that are traveling farther away from the optic axis, they're bent excessively, they're over-focused more. We have the beam waist, or the plane of least confusion. So if we add in correctors in the illumination system before the pre-field, okay, what we end up with is, right, out to some distance from the optic axis. And now we can't go as far as we like. There is a limit to this, but we can go some distance away from the optic axis, and we can get basically perfect focusing, okay, where all of those rays basically are focused to the same point on the sample, okay? So because of CS probe correction, we can get basically a twofold reduction in probe size, which results from a basically twofold increase in my optimal value of my semi-angle of convergence, okay? Okay, so if we look at a great example of this, again, using strontium titanate. So I have on the left an uncorrected image of strontium titanate along 001. There's your projected unit cell, and this is at 300 kilovolts. So if we add CS correction and then drop the voltage to 200, we see a massive improvement here, okay? So the difference in resolution between these, you're going from 136 picometers to 80 picometers as a result of this, okay? So And we also had to take the hit of going to a lower voltage, right? Because our wavelength got a little bigger, okay? But the reduction in the resolution, or the improvement in the resolution from CS correction, basically outweighs the increase that we got from the voltage decrease, right? So it's that much more powerful, okay? And that'd be interesting to calculate, like, where is the cutoff point that uncorrected 300 keV is actually equal to corrected at some other voltage. I think you'd have to go pretty low. I think you'd probably have to go down to, you'd have to go probably well below, because I think on our system, I think you can get 100 picometers at 60 kilovolts. So I think you'd have to go well below that before you equaled the uncorrected 300 keV resolution, just to give you an idea, okay? So that's the power of CS correction, right? Is we can get small probes and we don't have to make the voltage crazy high, okay? So some great examples of this, right? So we have some epitaxial growth on silicon. So we have a silicon substrate, and then we've got some epi layers on here, okay? And the whole thing's coated by amorphous carbon. But it's kind of hard to make heads or tails of these epi layers here, right? You can see I put a question mark there. So if we do HAADF-STEM of the same thing, this becomes way more obvious, okay? So we can see a bright band here, which is actually silicon germanium. We can see on top of that, there is a pure silicon layer. And then on top of that, there's a silicon oxide, okay? And then the amorphous carbon, okay? So you can see how much easier it is to resolve these with HAADF-STEM as opposed to high res, okay? Okay, and then we can go back to looking at the silicon dumbbells. So I showed this image previously when we were talking about high res, okay? And then if we put the projected silicon structure in here, right? Well, it doesn't match up with anything, okay? But if we look at the HAADF-STEM, well, look, we actually see the dumbbells, right? We see the dumbbells and they match up perfectly with the projected structure, okay? So this is the same model. I just changed the color to blue on the right because it just looked better than if I did the green. But it is the same structure and the same model as the one on the left. And both of these images, of course, are the same magnification as well. Okay. So again, HAADF-STEM gives us intuitive images that are indicative of the true atomic structure. Okay. It's a robust imaging technique. Okay, or at least more intuitive of the actual structure. Okay, I guess I know there are people out there that will say technically, and that's true. There are some instances where HAADF-STEM does not perfectly provide intuitive imaging, but by and large does. Okay, so then let's look at another instance of this. So if we go back to the calcium lanthanum sulfide, but the calcium lanthanum sulfide in this case was pretty thick. Okay, 200 nanometers is very thick to do any type of high resolution imaging on effectively, okay? Whether that's conventional, whether that's HAADF-STEM, okay? So if we look at the high res image of this structure along 111, that's not a good looking image, okay? We're seeing detail in there. Whoops, sorry. We're seeing detail in there, okay? If we took an FFT of this, we would see detail in the FFT, but that's really a very poor image, okay? The reason that this is so poor is that high res, to be effective, it relies on having strong Bragg scattering, okay? If the sample gets very thick, you have a suppression of the Bragg scattering, okay? So if you have a suppression of the Bragg scattering, it's going to be very hard to get a decent high res image from it. But if instead we take a HAADF-STEM image of the same thing, well, that's a big improvement in terms of what we can see, okay? And now to be clear, your HAADF-STEM images will be improved as the sample gets thinner, okay? But the point of this, though, is that even in a quite thick sample, okay, HAADF-STEM can still be effective, right? So you don't have to throw your hands up, right? If you're doing high res, the sample happens to be a little on the thick side, and say, you know, this isn't working, I can't get anything. It's like, switch to the HAADF, okay? And you probably will be able to get something, okay? And again, the reason is, right, HAADF doesn't rely on Bragg scattering. It relies on incoherent imaging, okay? Those electrons scattered to high angles where we don't have Bragg scattering anymore, okay? So this is still effective for imaging thick samples, which is great. Okay, it's another great tool to have. Okay, and then I already showed you this example of the diffraction from the zinc sulfide, and we see the diffraction pattern that indicates the presence of the twinning and the stacking faults is shown by the streaking. So if we actually take a HAADF-STEM image of this, we can actually see what this looks like, okay? And so this is really, really interesting what we're seeing here. So we're seeing basically changes in the polymorph of the zinc sulfide, okay? So the zinc sulfide, depending on how it's stacked, you can have different structures, okay? So you can have a wurtzite structure depending on how it's stacked. So that's actually what you're seeing if you look from right here, where my mouse is, to right here. This whole block is wurtzite, zinc sulfide. But then right here, there's a switch, and from here to here, it transitions and becomes zinc blende, zinc sulfide, okay? And then there's a single stacking fault right here. It goes back to zinc blende. Then we have basically like a a small region here where it goes back to wurtzite, and then it goes back to zinc blende, and then, yeah, so you can see, and there's another big region here of the zinc blende, and then this again becomes wurtzite out here, okay? So this is really useful, right? Because we can actually see the true atomic structure of the defects, okay? Which we can't really tell just by looking at the diffraction pattern itself. Okay, so CS-corrected HAADF-STEM is essential, okay? HAADF-STEM, as of today, is now the most important atomic res STEM imaging technique. So even though I told you that high-res TEM is the most important in terms of being essential, HAADF-STEM is more important in terms of its importance today, overall, technologically speaking, okay? It's robust. It gives robust, intuitive image interpretation that is more representative of your true atomic structure. It's relatively easy and straightforward to set up. You just need a single annular detector. You don't have to do any special image processing. You have the benefit of the z-squared sensitivity, so it's chemically sensitive, and you also have less of an issue if your samples are on the thick side, okay? And it is becoming very, very easy to get access to CS probe corrected STEMs, okay? It's becoming very, very common now. So just in the state of Florida, we have seen a pretty substantial increase in this. So back in 2012, the first one arrived at Florida State, and then we got the second one in 2020, and now Miami has one as well. So now in this state alone, we have 3 of them, okay? So I think in pretty much any state where you have like the flagship university, they are likely to have, well, and not necessarily, depends, it might be the private university, but there's likely to be a university not very far from you that has one of these instruments, okay? The CS probe corrected STEM, okay? So that's why it is essential. All right, and then last is STEM-EDS spectrum imaging. Okay, so just to briefly review this, so we're talking about the generation of characteristic X-rays. Okay, so if I have an atomic model of silicon here, and I take an electron from my my STEM, okay, it comes in and it knocks out a K-shell electron from my silicon, so I cause ionization, okay? What happens then is I get an electron from the L shell that drops down to fill the K shell, okay, because that is a very energetically unfavorable state, and that difference in energy is given off as an X-ray, okay? In this case, that would be a K alpha X-ray, okay? And the energy of that X-ray is equal to the energy difference between those electron shells, okay? And so that X-ray, if it's going in the right direction, will be detected by my EDS detector, okay, or energy dispersive spectroscopy detector, okay. In this case, I put SDD, silicon drift detector, because that's what all modern EDS systems are, is they use silicon drift detector technology. There is a couple examples here I'm going to show you that were not taken with that technology, that were actually taken with what's called lithiated silicon, okay. which we'll see here in a minute. But anyways, this is what EDS measures. It measures X-ray signal versus X-ray energy. Okay. Okay, so this is an example EDS spectrum that I took a long time ago, but I still like to use this as kind of my baseline example because it just has a lot of different elements present, and it shows a lot of this really well. Okay, so again, you have counts versus X-ray energy. So the peaks in the spectrum are characteristic of specific elements. Okay, so this is what we call the sum spectrum from the area in red on this HAADF-STEM image. Okay, so this is actually the gate region of an AlGaN-GaN high electron mobility transistor. Okay, right. So we see the the peak labeled by element and transition here. Okay. All right. So then, how does spectrum imaging work? So if we have a area of analysis that is made up of pixels, okay, and we have a STEM probe that's on one of those pixels, well, it's going to generate X-rays at that pixel, and those X-rays are going to be detected by my EDS detector, and I'm going to get a spectrum generated at that pixel, okay? So for each pixel in my analysis region, I'm going to have a EDS spectrum attached, okay? So my image, which is two-dimensional, becomes a data cube, okay? So the third axis of the cube is therefore X-ray energy, okay? So this is the heart of how spectrum imaging works, is that you have to think of this like a data cube, okay? So then, if I take a slice through the data cube, this corresponds to a range in X-ray energy, okay? And usually this corresponds to a specific peak in my spectrum. So if I look at this example here for this peak, this is just some nondescript peak. I don't know what this is, okay? So you can see between the dashed lines, I'm integrating under the spectrum, okay? You'll notice also that there's a little bit missing here, right? The blue doesn't go all the way down. The reason why is that this is background, and you don't want to include that in your imaging, okay? You want to remove that contribution, okay? So if we do this pixel by pixel, okay, and we take a slice, so if we take each of these, we do this for each pixel in this slice, okay, we end up with an image, okay? So in the case here, if we do this for the energy range that corresponds to silicon K. Now I put silicon K and not silicon K alpha because the way that the software does this is it actually uses both silicon K alpha and beta when it's doing this. So that's why I didn't put alpha, because strictly speaking, there is a beta contribution to this. Okay, so this would actually correspond to a couple slices, if you will, through the data cube. Okay, so as we go up in energy, we go to gold M. Okay, so we can see, right, as we're going where we have the gold, right, we're going to see more signal. Okay, we have the nickel K, so that's actually what that gray stuff is underneath the gold. And then we also have gallium K, which is basically everywhere in my GaN, or my AlGaN-GaN epi layers, okay? All right, so we can use this, right, to spatially orient each of the elements, right? So we can spatially resolve the X-ray signals and figure out where the presence of each element is relative to everything else, okay? So that's our reference image on the left, okay? And that is the area that we're doing the spectrum imaging, okay? So the zone axis B11 bar 00, that corresponds to the GaN specifically, okay? And so if we look then at the maps, okay, so for the gold L, gallium K, nickel K, silicon K, aluminum K, and oxygen K alpha. You'll notice with the oxygen K alpha, I did put the alpha. That's because there is no beta peak for oxygen, okay? So in that case, it is appropriate to list that specifically as just K alpha, right? So now, if we overlay these, we get this nice rendering, okay? And we can see where everything is relative to everything else, okay? So this was not taken with a very fancy EDS system. Okay, this was a far more primitive system compared to the one we have now, but you can still see, even with this system, we're able to resolve that there's aluminum pileup right on the surface of the epilayers, and we're able to see this oxidation layer right on the surface, and that actually surrounds the underside of the nickel. Okay, so, and that's what they, again, a more primitive EDS system. This was back from 2018 when this data is collected, but I still like to show this to this day. Okay. All right, so if we look at some more modern examples here, so we have some presumably core shell structures. Okay, so palladium cores surrounded by ceria, okay, shells. Okay, so this is the HAADF-STEM image of two of these. Okay, so now looking at the HAADF-STEM image, it's not very obvious that we have a core shell structure here. Okay, but when we do the mapping of the three elements, right, it becomes very obvious where everything is located. Okay, and then again, we can put everything together and we get the RGB composite. Okay, so this is an example that really shows the importance of why imaging alone often isn't enough. Okay, so just by looking at the image, it really wasn't very obvious that we had a core shell structure, and we really had no way to know where the palladium was relative to the ceria shell. Okay, but by adding in the STEM-EDS SI, we ended up getting a more complete characterization. Okay, and this was done on a much better system, okay, than the one that was used for the previous example with the algan-gan HEMT. Okay, we can look at another example. So this is iron oxide nanoparticles coated with silica, which has a very thin coating of carbon on it. Okay, so again, here's the HAADF-STEM image. Okay, so it's fairly obvious looking at this. I can see the iron oxide and the silica, right? That's fairly obvious by looking at it, but it's not very obvious as to the presence of the carbon shell. Okay, so again, right, to get a complete characterization, we can go to the STEM-EDS SI. Okay, so if we do this for the silicon K, the iron K, and the carbon K alpha, again, because carbon K does not have a beta, and then we overlay them, we can actually see the shell there. Okay, so the carbon shell was actually there, even though it wasn't very obvious in the HAADF-STEM image. Okay, and then here's another good example, again, going back to the calcium lanthanum sulfide. So in this region of the material, we see a rather interesting microstructure here. Okay, so near the surface, we see there's a lot of porosity, right? And we see what looks like some fairly fine, some regions that have fairly fine grains, and then the grains tend to get bigger as I move away from the surface, which is denoted by the S. Unfortunately, you do see these vertical streaks, which is due to curtaining from the fib prep, which happens whenever you have porosity like this. So it's kind of hard to, get around that per se. But the point is, right, it's a kind of a complicated microstructure, okay? And unfortunately, just by looking at the image alone, we really don't have a clue as to what this tells us chemically, okay, or elementally. But if we then map some of these elements, okay, we can see that we have a very oxygen-rich structure, or oxygen-rich where the porosity is, okay? And then we actually see that under the porous region, we have a region that is rich, or I shouldn't say richer. It's depleted in calcium, right? And then beneath that, it is not depleted in calcium again. So there's actually three zones of material here, if you will, right? So if I do the overlay, you can see, right, there's this zone here, which is sulfur and calcium, and then this blue area, which is mainly sulfur, and then the surface area, which is oxygen rich, okay? And again, we really couldn't have told any of this by just looking at the HAADF-STEM image itself. Okay, and of course, these images I've showed you up to this point, these are fairly coarse scale, right? You can see this is 2 microns. The one previously, these are like nanoscale. We want to really push the limits here, of course. So can we do this at the atomic level? So if we look at, good old strontium titanate again, right? There's the projected structure. There's my HAADF-STEM image with the projected structure superimposed. So if I do the EDS maps, again, oxygen K alpha, titanium K, and strontium L, okay, and then I overlay it, I can see the same thing, okay? I can see exactly where I'm expecting to see what I'm expecting to see, and we can actually now see the oxygen columns in the composite map that we couldn't see just in the HAADF-STEM image alone, okay? All right, here's another example of atomic resolution work. So these are in-gas indium aluminum arsenide superlattice photonic structure, okay? So there's the HAADF-STEM image on the left and viewed along 110, so you're seeing dumbbells, okay? So if we look at the maps for these 4 elements, okay? Aluminum, arsenic, indium, and gallium, okay? And then we overlay them here. So one of the interesting things we see is that we have the arsenic sublattice continuous as we switch between the 2 layers, right? So as we switch from the in-gas to the indium aluminum arsenide, we have perfect continuity of the arsenic sublattice, okay? Which is we would probably expect, right? Because they're both arsenides, but we can actually prove this by doing this mapping itself, okay? All right, so STEM-EDSI is also what I consider to be among these 4 essential techniques. Is the fundamental compositional analysis technique, tells us what elements are present, minimum detectable concentration. So, I mean, that's there is a limit, of course, to what we can see with this, right? So, if somebody comes in and they're looking for things that are, fraction of a fraction of a fraction of an atomic percent, that, of course, is, has a limit here. My understanding with this is, with sufficiently long counting and whatnot, and I mean, there's improvements in the detectors, but you can get below an atomic percent, okay? Again, with the right equipment and, enough time, okay? But what elements are present? Where are the elements located, okay? How precisely can they be located, right? So we saw lots of examples, or 2 examples of atomic resolution, right? Where we could resolve them with, basically angstrom precision, okay? So when you take CS probe correction with a good EDS system, right? You can have routine atomic resolution STEM-EDS-SI. Although strictly speaking, you don't need CS probe correction to have atomic resolution STEM-EDS-SI, okay? So as far as accessibility, every modern STEM is going to have an SDD on it now, okay? These are basically just like standard equipment on these systems, okay? And the other cool thing about this is that SDDs are rapidly improving in terms of collection efficiency. Okay, so back in 2012, the state-of-the-art collection efficiency was around 10%, meaning 10% of the X-rays emitted from the sample would be collected. And today, we're getting closer to 25%, okay, which is massive, okay? For the longest time, we were dealing with collection efficiencies down around 1 or 2%, okay? Before SDDs started becoming more apparent. Okay, I think in the data I showed you that I took with the lithiated silicon detector, with that system, that was probably around a 2% collection efficiency. Okay, so we've come a long way, certainly, with this. So, and that's why STEM-EDS-SI is essential. All right, so just to recap, okay, so we talked about high res leading off. In my opinion, that is the basis for everything else and the most important technique, okay, as an essential technique. Okay? And then we went to selected area diffraction and its importance as a structural analysis technique. Then we went to CS-corrected HAADF-STEM, which is becoming more and more ubiquitous and which has replaced high res as the preferred atomic resolution imaging technique. And then lastly, we talked about STEM-EDS spectrum imaging, okay, as a way to do elemental analysis and tell you what elements are present and where they're located, okay, because that's what, big question, right, when people come in, okay? they have material and they say, I have this, I have this structure. I want to know what elements are there and where they're located. Okay. So just to finish up here, okay, if you have any questions, you want to learn more. So as always, you can send me, email directly. I would appreciate it if you have questions about this webinar, if you please locate or put those in the comments section so that everybody can see those. This, of course, is the link to my YouTube channel. If you're watching this on YouTube, you're already on it. So, it's kind of redundant. But aside from that, I would like to thank you for your attention and support. And I apologize that it's taken this long to get this up, but I knew I couldn't leave you people hanging. So, thank you for being patient with me, and hope you enjoy this belated webinar. So, all right, with that, I hope your microscopy is going good in 2024, and look forward to getting out more videos for you very soon.